value given to you. Well, a lot of times when we get to the actual geometry proofs, you're going to be given stuff that have definitions. So if you look at, I grabbed the wrong one. If you look at the back of your reason bank, on the back of the reason bank, there's a lot of definitions at the bottom there. And what I want to do is talk to you guys about how we can take these definitions and use them into what I call a progression. The reason I use the term progression for these things is because I thought of it in terms of like football reference. A quarterback is looking down the field at different parts of a play. Which one of them is going to work for the situation? Well, that's why I use these things. Because we're going to have 15, 16 different things to look at depending upon information given to us. When we know that information, if we have this stuff written out in such a way that it makes sense, it's going to be very easy to follow. And believe it or not, probably about halfway through using this thing, you won't be looking at it anymore because you know it. It's also it's a forceful way to make you guys study this stuff as well. Okay. Real fast, I do have calculators still in case you guys still have to buy them. We have plenty of them. We haven't sold out yet. So one of the first ones that I like to talk about, because everybody knows what this is if you're given a midpoint.
Can we put this in one square?
Let me write this out first, and then I will explain to you how you would write it in. Okay? The way that I have these things filled out, the way that I fill them out is like this. On the top, it would say if I'm given a midpoint. It doesn't say what the midpoint is, it's a midpoint of what segment or anything along those lines. It's very generic. It's very vanilla, if you will. But what does a midpoint do? It splits it into what? Two congruent, well, segments, right? Because that's what we're dealing with. So what I'm saying here is that if I'm given a midpoint, I would state some segment is congruent to some other segment. Now, if you think about that, that's kind of like a condition. Remember the conditional statements using a definition? If you're given a midpoint, then you have two congruent segments formed. That's what that means. So in terms of a two-column proof, usually the way that I would put this then is that for each one of these progressions, I'm going to use some sort of example. And I would say x is a midpoint of AB. I would say that would be given. Well, if that's given, it would look like this. If x is a midpoint of AB, what two segments are congruent to each other? AX and XB. So that would happen, which means if I know that I have a midpoint, what's something that I can say about it? Well, some segment is congruent to some other segment. What segments are they? And what did you just use? The definition of a midpoint. That's how these things work. What we're using is bouncing back and forth between a definition into some generic statement. So if I'm looking at, well, this one here says angle bisector. If I have an angle bisector, what do angle bisectors do? What do they create? They create two equal angles. So I would say something about two different angles. Here I have this midpoint. So what do I say? Something about segments. These progressions are what's going to help you later on as we start to do these proofs. How do you use definitions in a sequence of statements and reasons? So what I want you guys to do is start with this. Pick a square, any square, it doesn't matter. If you're doing vertically or you're doing it horizontally. We're going to fill in about 7 or 8 of these today and just kind of walk ourselves through. That way as we start with some of the geometry, start with some of the algebra, we're going to be able to use your algebraic reasonings into geometric parts. These next few weeks or so, whether we're dealing with this chapter 2 stuff into chapter 3 and 4 and so on, when we start doing a little bit more of our triangle things, it's very important that we still have and keep these two sheets. They're going to be like, it's like your answer key for everything. What's really going to change a lot of times are just letters. The concept, the definitions, that's what you're just reusing over and over again. Okay? So you're going to have basically everything you need to know in front of you. Which means, should you ever want to lose this sheet? No. So here's a great idea. Create a backup file of it. Well, how do you do that? I don't know. Use your phone. At the end of the period, each day when we fill these things out, take a picture of it. Delete the old one. You know what I mean? That way you always have an updated version of what you have. So in case you do lose it, you can just get a blank copy of this from me and refill it back in from what you already had. Does that make sense? You're making your own backup file. That way you don't have to say, oh man, lost all my stuff. Then you have to go borrow someone else's and theirs wasn't as nicely written as yours. I'm not saying yours is bad either. But, you know, stuff like that. Take a picture of these things. Make a backup file. All right? That's what I'm telling you.
Black market.
Yes. So then, just like I did a second ago, I'm always going to write out some generic form of it. It's not always going to be the same letters. It's not going to be that. We're not always going to, every time we have a midpoint, it's not always going to be X as a midpoint of the segment AB. There's always going to be different letters. But the idea here is that it's still showing that something happened. And we're trying to write out how does it work in terms of a proof. And that's what that works. Okay? So write that into one of your squares, and we'll go through the next one that I have, the next one, which is very, very similar. When you have a midpoint, that is just a point that's the middle of the segment. But what about a segment bisector? What's the difference between a segment bisector and a midpoint? What's the difference? Just had like tests and stuff on all this not too long ago. What's the difference between a segment bisector and a midpoint? Does it have to? What's the difference between a segment bisector and a midpoint? I don't know. Is it possible that the definition of it is? They both divide it into two pieces. They both divide it into two equal congruent pieces. But I don't know. Do you think there might be a definition of it on your sheet of paper right in front of you? Huh. Yeah.
Oh.
Let's make another one. I will tell you this, guys. First semester geometry, you cannot forget anything from the day before. You cannot forget stuff from the previous chapters. It's not like other stuff where it's completely different topics. Everything that we use, we just keep building on it. We always, it's how math works. Okay? So let's look at one if we have a segment bisector. Remember, a segment bisector is anything that intersects a segment at a midpoint. So a segment bisector could be a point, a line, a ray, segment, could be anything. So basically it does the exact same thing. The only difference is that instead of being a definition of a midpoint, we'll say it's a definition of a, what kind of a bisector? Segment bisector. That's it. Segment bisector creates two congruent segments. Does the same thing. So you would state some segment congruent with some other segment. Well, what would that look like? Let's say XR ray is the segment bisector of AB. Well, when we had chapter 1 stuff, and also the very beginning of chapter 2, we drew a lot of these examples. Now, most proofs will come with a diagram. The stuff that I'm filling in on these little progression sheets, since I'm just doing like these one little pieces here and there, you're gonna kind of have to come up with your own pictures of them. So if array is XR, what's the endpoint? X. X is the endpoint because it doesn't have the arrow over it. Now, if it's the segment bisector of AB, AB is my endpoints. The XR just hits it in the midpoint, hits it in the middle. Doesn't matter where it's going. It doesn't necessarily have to be perpendicular. That's something completely different, which we'll put on here eventually. But if XR is a segment bisector of AB, what are the two segments that it created? Well, it's kind of dumb luck. I didn't realize I used AX and B again. You get two segments, AX and XB. So this one was given. That's the definition of a segment bisector. You're using a definition to show how something works. Over and over and over again. It doesn't change. What other kind of bisector do we have?
Angle bisector.
Angle bisector. What do you think an angle bisector does?
Bisects.
Congratulations, it bisects an angle. What does it create?
Two
Equal or congruent angles. Exactly. So let's write one out for that. I'm sorry, I got a little ahead of myself here. We'll give you guys a second to catch up and we'll do an angle bisector. Oh, excuse me. People have been asking me throughout the day today, when do I know when I have to fill in one of these squares? Usually it's going to be when I say, put this in a square. Or I put a square on the smartboard right when I start filling it in. That usually means make sure you put it on, make sure you put it in one of those. Okay. So we'll do the same thing for angle bisector. We'll go through the same idea if we're given an angle bisector. Well, segment bisectors created two congruent segments. What do angle bisectors create? Two congruent angles. So what do you think you're going to state? Angle, congruent, angle. Now there's a reason, we'll get into the differences between using congruency and equality here in a little bit. It's okay, that's all right. Congruent is more formal. Congruent means equal length. When you're doing the algebra stuff, everything should be in equals, but sometimes it asks you to put things into congruency. And there's a very easy one-step way to do that. And I'll show you guys that here. We'll put that as our last one for the day. Example. Let's say that we have ray BD is the angle bisector of angle ABC. Let's say that's given to us. Again, I'm just using very generic terms, very generic write-ups. They don't not every angle bisector you guys see is going to be BD. It could be XY, it could be WR, doesn't matter. Okay? But the idea here is that it's just some generic write-up. So if that's given to you, Angle bisector creates two congruent angles. According to my diagram, what are my two congruent angles?
ABD and DBC.
Perfect. So if I have an angle bisector and I know all my letters, I just do this. Angle A, B, D, congruent. Angle B, D, C. What definition did you just use? That's it. And make sure you write definition though. Definition, angle, bisector. Okay? Starting to sense a pattern. If you're given something, you're using that something's definition. That's how these things work. Anytime you're given something, you're going to use their definition. That's how it works. That's how all these geometry proofs work. You're terrible so far. What do complementary angles do? What do supplementary angles do?
180.
Okay, let's do that. If you're given complementary angles, it's not just that the angles are nice to each other. You know how many, well, first of all, you know how many angles there are and what they have to add up to equal. So how many angles are there if they're complementary angles? Two. And then what do those two angles have to add up to equal? 90. What is the most generic way to say two angles add up to equal 90? You're making it more tough than you need to. What's the most generic, vanilla, basic way to write two angles are add up to equal 90?
Angle.
Isn't that the most generic way to write it? But the only reason that I don't say angle 1 and angle 2 is because what happens if it's angle 4 and angle 6? You know what I'm saying? I'm just getting at the idea that you could have, I don't want to set it up in such a way that it won't work because of the way something's lettered. I'm writing these in hugely generic format. Angle plus angle is 90. And you're okay by saying it's one angle plus another angle, two angles that add up equal 90, but in the generic basic sense, you know you have two angles, we have to add the 90. It doesn't matter what they're called. Angle potato and angle tomato. It's 90. Here's how it would look. Given angle 2 and angle 3 are complementary. We know that two angles that are complementary add to equal 90 degrees. 90-degree angles form what kind of angles?
Right.
Correct. When I draw a picture of a right angle, what does it always have? A little square there. Does it state what angle 2 and angle 3 are equal to each other?
No.
Could they be?
Yes.
Do we know?
No.
No. So all I have to do really is just draw that. Call one of them angle 2 and call one of them angle 3. That's what that diagram would look like. I don't know if it's correct, but in the essence that I have two angles that are complementary, I know that those two angles next to each other sharing the same vertex add up to form a right angle. Algebraically then I can say, according to my definition, angle 2 plus angle 3 has to equal what? 90. What did you just use? What's your reason for writing that? It's like a broken record, isn't it? That's what that looks like. So later on, when we get to a proof that says stuff about angles being complementary to one another, you cannot tell me, I don't know what to do. And I'll say, yes, you do. Because you do have nice handwriting. I give you a compliment. Anyway, but no, you know what to do because on your progression sheet, hey, Murphy told me to write this down because if I'm given complementary angles, I know that this stuff has to happen. So I can write at least something down to get me started. Okay. What's going to change in here for supplementary? That's it. That's really it. Let's go through that one. Now, honestly, one of the reasons why I came up with this idea of making this progression sheet is that I saw for so many years, so many of you guys have a hard time getting your thoughts on a piece of paper when it comes to a proof that makes any sense. But if you say your way through it, you can get through it. But having to write that to paper, it becomes rather difficult. By using this method of this progression sheet, it has all the correct terminology and the correct vocabulary written down on a sheet of paper in an algebra, in a geometry sense that makes sense to write out a proof. So that's kind of one of the main reasons why I started to go through these sheets. And I've had some pretty good success with some of these things over the past couple of years as people start, believing that I'm trying to make you guys do well. So we know that some angle plus some other angle is 180. Example-wise, we'll say angles 1 and angle 5, I don't know, are supplementary. In some sort of a diagram, supplementary angles have to add to equal how much? 180. So here's angle 1, here's angle 5. They form a line. Okay. That's what that looks like. Do supplementary angles have to be adjacent?
No.
No. What do have to be adjacent?
The vertex?
No.
No.
Okay, fine. Linear, all right. Yeah, linear pair are the ones that have to be adjacent, because they're the ones that have that common vertex as their opposite rays form lines and stuff. So, supplementary don't necessarily have to be. So here we have angle 1 and angle, oops. One big thing to remember, don't make your own abbreviations. Don't make up your own reasons. Don't just say, oh, it's because of this.
So I did.
A lot of people make up stuff all the time. Whenever you make something up, you're probably going to be right. Don't make stuff up. Don't. It's not worth it. Okay. Don't just don't fill in the space because you think you need to. It's just another way of doing it. Everybody teaches a little bit differently.
Like he just told us to memorize it. He didn't even let us like use abbreviations. He just writing it down.
Everybody teaches a little bit differently. Okay? Everybody's a little bit different. All right. Now, the next one I'm going to do is linear pair. Linear pair are adjacent supplementary angles. We know that linear pair are ones that add up to equal 180 degrees as well. But more specifically, they are adjacent supplementary. So what we do with a linear pair is we're going to take 2 steps to use up that given. Sometimes a given statement, you're only going to have 1 step after it. Sometimes you'll have a given statement that you could probably use 4 steps after it. For example, just one we'll get to later on, is that? Perpendicular bisector. If you have a perpendicular bisector, what happens? It bisects a segment and creates 90-degree angles. So what happens here is that what we'll get to, I don't know if we'll get to it, we might get to it tomorrow, if not tomorrow, Thursday. For a progression like this, we would start with the given. We'd say that two segments were congruent. Then we'd say that we have right angles. And what do you know about all right angles? They're all 90 degrees, which means right angle is congruent to right angle. So you can actually say there's 4 steps that you can write out when you're given this. So if you're given that, you're going to look at your sheet and instead of saying, I don't know what to do, can you help me? I'm going to tell you right then and there, what's your sheet say? And that's what you have to look, that's what you have to work on. And I'll say, that's your fault. Okay? I'm telling you guys, these things are going to be so helpful for you as we get throughout the next couple of months, okay? So let's look at linear pair. That's what it was. If given a linear pair, we're going to do this in 2 steps. If we're given a linear pair, first thing I want to do is state that angle and angle are supplementary. And then once you, oops. Accidentally deleted that. There we go. So what we're going to do is we're going to switch from something that we didn't know anything about to something we know about. What do you know about supplementary angles? What did we just write down? What did? How'd you write it down? No. Angle plus angle is 180. Since we already know that the angles are supplementary, then I would say angle plus angle is 180. So what you have here is there are going to be 2 statements that you can make out of it. The reasons are a little bit different then. So if given, let's use x and y this time. X and y are a linear pair. And let's say that's given. If angle x and y are a linear pair, that means that those 2 have to be supplementary. Okay. So according to my progression, it says to state that those 2 angles are now supplementary. So according to the example, which ones are supplementary? X and y. And what do you think my reason is?
Definition of linear pair.
Exactly. Hey, now we have something about supplementary. According to our progression sheet, if we know something's supplementary, what do you write down now? Go back to look at it. Yep, in this example, it says to say that angle plus angle is 180. Well, what are the 2 angles that I'm using in this example? X and Y. So my third step then would be
And then would that be the definition of supplementary?
very good.
This box is bigger than ours.
I know, and I know that some of these things you might have to use 2 of them and just kind of over highlight it or whatever. I just try to make them so they fit as best I could. So in this case, notice all we did here is that we still have linear pair on the left, and then all of a sudden linear pair on the right. Supplementary on the left. Hey, look what's on the right. Supplementary. they're always, more often than not, one step away from each other going down the diagonal as you're going through this. That's how proofs work. We use them in such a way that your statement is generally something given to you. That given part has some definition that you can utilize. Whether it's an angle bisector, a second bisector, a midpoint, something along those lines, there's always going to be something there. Okay? Again, if I had to draw an example,
I like drawing examples when you
x and y, these two would have to be 180, okay? Something along those lines. Meh?
Can I I'm just gonna do this. Oh, no.
What's that?
You say you can highlight it. No,
Yeah,
I
whatever
don't
you-
want to take up 2 boxes.
No, whatever you need to do, because you're going to see that some of them are there's less stuff for some of the other ones than there are for
I'll find it.
I mean, this perpendicular bisector is going to take probably 2 full boxes to fill it all out, because there's a lot of info you can do with that. Can I show you another style real quick?
Sure.
We can still use it with our progressions. That way you have it there. So what is this one now?
What's what it do?
23? Oh, sweet. Oh, it's 7 minutes or something. No problem.
Is your clock?
No, it really is 6 o'clock.
Oh, this is it. Wait, what did it say?
What does segment addition mean? What does segment addition mean? You're adding 2 segments. What's the only rule about segment addition you have to worry about when you're adding 2 segments? Where do those 2 segments have to be? On the same line. They have to be collinear. So for segment addition, yes, I'm going to put segment addition, and then in same box I'm going to talk about angle addition. Just one little heads up, things to look for, because we're going to use these a lot in the next couple of days. In segment addition, the only rule you have to be is collinear. But remember, it means segment plus segment equals segment addition. Segment plus segment equals,
Line.
no, a bigger segment. That's all that means. And then when you deal with angle addition, there was one rule about angle addition. Angle addition had one rule as well. In order to add 2 angles together, they had to have something in common. Not angles, they have to have the same vertex, very good. They have to have a common vertex. And then angle addition was angle plus angle equals bigger angle. Okay. Now, in terms of what is this going to look like in a geometry style versus the algebra stuff that you guys did last week, which you guys did really well on, is that it's going to look a little bit like this. It's on a clean sheet here, so you're going to be given information like this. You have a segment AC, but the given statement says AC equals AB plus AB. And it wants you to prove that AB equals BC. So in terms of algebra and geometry, we start to mix them all together a little bit here. Very first thing you always do with any 2-column proof is to write down your given. In this case here, we are given AC is AB and AB. Is that what it says in the diagram, though? What does the diagram say? What would the segment addition be for the diagram to show that AC is equal to something?
AB plus BC.
Right.
plus AC.
Yeah. According to the diagram, though, AC is made up of AB plus BC. What property did I just use? What did you just add together? Segments. You just used segment addition. Because segment addition says collinear points, too small or equal the whole. Now, do you have AC represented as two different things? Think of it this way. If x equals 9 and w equals 9, what can you say about x and w? They equal the same because they equal the same number. Don't these two equal the same thing?
Yes. Yeah.
So what should those two equal? Each other. See how these two are just equal to AC? They're both equal to AC. By putting them equal to each other, you're just using the same idea as this. You're substituting in one for another. Putting in something for something else is called substitution. Look at what you have to prove. You have to prove that AB equals BC. What do you have on both sides of the equal sign of the algebra right now? Aren't these the same on both sides? How do you get rid of them? If I subtract them from both sides, what are you left with? What property did you use by subtracting the same thing on both sides of an equal sign? And this is where we're going with this.
Well, okay.
That's where we're going with this. By subtracting the same thing from both sides, using the algebra stuff from last week, we're throwing it into segments. We're throwing it with angles. We're just using the same things as the algebra. The only thing that's different, instead of solving for x, we're using a lot of letters. That's it. That's it. Okay. Where I place the homework for tonight, I have it. If you go to the chapter 2, the chapter 2 tab, it's on the calendar, and I put a link on the calendar also. I want you guys to do the 2.6 practice B. I want you to do these first two fill in the blanks. All the reasons and some statements are all kind of thrown in here. I want you to rewrite these two and figure out why they did what they did. Using your progression sheet, using your reason banks and stuff. Those two questions, okay? So I want you to write these two out. Because obviously you can't write it in on the Chromebook. Would that work? I want you to write these two questions out. Go through the statements and reasons, figuring out why they wrote down what they did. This is kind of a fill-in-the-blank style. This is where we start a little bit with these, so as we start to get accustomed to how it works. Okay? You're using the algebra properties a lot, substitutions, and you're using a little bit of that geometry. Okay? Get those two for tomorrow, and we'll build out of it after that. Okay?
I got it back that day.
That's fine. Yeah, no, that's fine. I'll fix it. I never screw up. You know that.
Right. You put my quiz in.
I know, right? That happens. That does happen all the time. You'd be surprised at how many times.
Why haven't